All right, good afternoon, everyone, and welcome to the Office of the Chief Scientist Science Seminar Series. My name is Andrew Paul, and I'll be the host for today's seminar. On behalf of the entire OCS team, we welcome you to today's event. In the spirit of reconciliation, I'd like to start with acknowledging that we are on the traditional lands and gathering places for Treaty 4, Treaty 6, Treaty 7, Treaty 8, and Treaty 10, as well as the homeland of the Métis peoples. I think today's presentation on Lake Sturgeon provides a great opportunity for us to think about this land acknowledgement. We can thank First Nations, Inuit, Métis for sharing this cool and ancient fish with ourselves, so that it's something that all of us can experience to this day. The purpose of these science seminars are to provide an opportunity to improve our understanding of Alberta's environment and to put knowledge into practice through evidence-informed decision-making. If you have questions today or comments, please enter them at any time into the chat window. Your video and audio has been disabled, so we'll have to do the dialogue through the chat window. We do that to maintain call quality. So after the presentation is finished today, I'll read out the questions and comments in the order that they were received. So with that, I would like to welcome today Dr. Stephen Spencer and Dr. Inesh Munaweera, and they're going to be presenting on leveraging citizen science data with advanced statistical models, recent updates on Lake Sturgeon monitoring in Alberta. Stephen is a fisheries biologist that has worked for the Alberta government for over 25 years. His interests include fish population ecology and working with stakeholders to incorporate biology into fisheries management. Stephen says his work is never boring as a fisheries biologist in Alberta, given its rapidly increasing human population, relatively few water bodies, and a short growing season for fish. Inesh is a postdoctoral researcher at the University of Alberta. He specializes in applying Bayesian statistical models to fisheries ecology. His research focuses on solving real-world challenges in fish population dynamics and conservation. He collaborates with government agencies and academic institutions to deliver actionable and data-driven solutions. And with that, I'm going to turn it over to Dr. Spencer, who's going to start off the presentation. So thank you, Inesh and Stephen, and over to you guys.
Thank you, and thanks for the introduction. I typically work more with pike and walleye, but Lake Sturgeon, I feel honored to be working on some of the difficult problems that have come forward for Lake Sturgeon conservation. They're an important fish. They sure are an interesting one. They live a long time. Very important to our Indigenous peoples. The Ojibwe around the Great Lakes call them the royal fish, and in Cree, their name is Namao, which is also the name of a town nearby, Edmonton. So as far as an outline, I want to introduce sturgeon and some of the recent troubled history that has caused their population declines. I'd like to highlight our program with citizen scientists. It's been very successful. It illustrates some of the challenges of estimating numbers of a low density species that is over in a river over a long distance, and the external review on the science that we were doing and how that affected what we're doing. From there, I'll pass the baton, so to speak, to Dr. Inesh Munaweera about the innovative population modeling he did, and then finish up with future projects and possible outcomes. So sturgeon are really an ancient fish. Like, they evolved a long time ago. The fossil record goes back 200 million years. You see that rock-like picture in the bottom corner there, it's a 72 million year old sturgeon skull that was found in the Edmonton River Valley back in, I believe, 2023. They've been around a long time and successful, having lasted that so long, but they're vulnerable due to a biology of late maturity. So they're kind of like us. They don't really mature till their late teens, early 20s, and then they spawn infrequently every 2 to 7 years. And so as a result, they have to live a long time to keep the population going. So their longevity is an estimated 100 plus years. They're affected by overharvest, pollution, and dams can really affect populations. And so globally, not just in Alberta or North America, across the Northern Hemisphere, sturgeon populations have seen large declines. Excuse me. So just to highlight this picture down here, sturgeon get to quite a large size. This I found this at the Manitoba Museum. This is an exceptional fish. The record says that it was over 180 kilograms and 4.6 meters. That's very unusual from what I've seen in recent years, but individual fish do get over 100 kgs, but very rarely. The really huge fish you see on the in photos are typically white sturgeon or beluga sturgeon in Russia, but yeah, Lake Sturgeon typically are smaller. Looking into the Alberta file, just reading through some of the archives, there was a history of restrictive regulations. There were several harvest closures to try to maintain numbers, but the numbers continued to drop. I found this photo. I believe this is the Alberta Lake Sturgeon record caught by Mr. Muscovich. The report said it was about 47 kilograms or 105 pounds. Maybe it's the angle of the photograph, but Mr. Muscovich probably wasn't the tallest guy. So continue along with the history of the what occurred as far as to sturgeon in the river, in the North Saskatchewan River. The fish disappeared for a period of time, and we got this this graphic, and this is pretty neat. It's hand drawn graphic, so it was an old graph that was updated, but got it from the city of Edmonton. And on the y-axis, this is a measure of oxygen, and so 5.5 is the CCME guideline. That's the Canadian Council of Ministers of Environment. So I'd like to see oxygens above that for aquatic life. And on here is also 3, which we really sort of say is, the minimum. And as you can see in the 50s, the river would go anoxic. So the x-axis is miles downstream from Edmonton, and these were the oxygen records. So this seemed to be some evidence that that's probably what that really dropped the numbers in the North Saskatchewan River, that untreated effluent would caused anoxia in the water, and that would have killed fish for long distances down from Edmonton. But as treatment improved and water flows actually increased from the upstream dams, because the releases during the winter time, we saw oxygens get much better, and now their winter oxygen is quite good, and it's not the limitations that it was. So seemed like evidence of why sturgeon disappeared completely from the North Saskatchewan River for a period of time. I just want to pause here. The gentleman lovingly letting this Lake Sturgeon go after he's measured it is Daryl Waters. He was the original Sturgeon General. He devoted a lot of his career to working on Lake Sturgeon, and his holidays he'd take down south and we'd collect information on the South Saskatchewan River. So in the North Saskatchewan River in 1990, someone came into the Edmonton office, is what the story was. This is before I started, but described a fish that sounded a lot like a lake sturgeon. People sometimes would misidentify odd, like suckers or something, but this seemed pretty good. So the story is that that evening, field work started, and started working on Lake Sturgeon in the North Saskatchewan. So in the early 2000s, sturgeon were listed provincially as threatened under our Wildlife Act. And then COSEWIC, who provides recommendations to the federal government for listing under SARA, has recommended in 05 and 17 that populations in the Western Hudson Bay zone, which is where we reside as far as sturgeon are concerned, recommended as endangered. The recovery objective, what we want to do for our work is to quantify and increase population levels of lake sturgeon in the North and South Saskatchewan rivers. So that's what we want to do. So more on lake sturgeon. They live in our rivers despite their name in Alberta. They certainly live in lakes in other jurisdictions, but here they're primarily in rivers. The photo at the top in the middle here, this is someone from our Red Deer office. It's kind of an interesting story. There was a flood, I believe around 2012, and the Red Deer River flooded its banks, and some fish got pushed out, and our office got a report of something very large swimming in a golf pond. And so the Red Deer crew went out and rescued this fish and put it back in the river. But that must have been quite a shock golfing and then seeing something that large swim by you as you try to retrieve your golf ball. But, yeah. So sturgeon, they're tough to study because they can move long distances, and they have a huge area that they can live in. So as far as the North Saskatchewan fish, probably this furthest upstream I would classify as Lake Sturgeon habitat would be Drayton Valley. We do get fish going a little further upstream occasionally to Rocky Mountain House, but I think for the most part that's not really fish habitat. So downstream of Drayton Valley, fish can swim without any barriers to their movement to the forks where the North Saskatchewan River and the South Saskatchewan River come together here, and even move upstream to the dam on Lake Diefenbaker. So huge range, and we do see the occasional fish making larger movements. Typically, though they live most of their year within about a 70-kilometer home range. The South Saskatchewan fish, they have the Old Man Dam and the Visano Dam as their upstream limitations. They're found mostly downstream of Lethbridge, Ward Medicine Hat, and we also get them in the Red Deer River, and they could swim into Saskatchewan unimpeded to the Lake Diefenbaker Dam, and we've actually seen fish move through the dam and move into the North Saskatchewan, but that's pretty rare. So that bounds the two populations, the North Saskatchewan, the South Saskatchewan River. So how do you study a fish that moves so far and lives in so many different habitats? And angling has, through trial and error, we found to be by far the best way to study fish. Electrofishing and nets aren't that effective at catching fish, and the unfortunate thing is you can actually kill or injure fish, what we certainly don't want to do. Lake sturgeon have a protrusible mouth that seems to be very tough, and fish. I've never really seen a lake sturgeon get injured angling, so it's very nice that we can use that as a tool. If fish are handled well, as this angler is holding the fish in the water and releasing it carefully, not holding it up in the air for pictures, their backs aren't well supported. This is what we're recommending, and it's fish do very well if they're handled well. So we have, we're very fortunate to have passionate anglers that have donated their time to us. These citizen scientists, they're very skilled anglers. I sort of think of myself as somewhat good of an angler, or somewhat proficient at angling, but I've been out with these volunteers, and can they catch fish? And so we get lots of interest. We've actually pared our group down to a very small number of people. We're down to 5 people now, whereas in the past there's been as many as 60. But the chasing after logbooks or equipment was a challenge. So right now we have fewer people, and what I hear from the volunteers is, we're already out there, so I might as well be helping you. So the citizen scientists we train, or I mean, they're very good at catching fish, but for our purposes, we wanted to show them what measurements we needed, and they enter their data online now, so it can be instantly up in the cloud and accessible, so we can see how things are going. We provide equipment to the citizen scientists, readers, so that they can read the tags that are injected under the skin of the fish. They're provided slings for safe handling, and they encounter a lot of people on the river, so they're provided with messaging. So that's been very helpful for us. They get collection permits. We give them that permit so they can fish an extra rod or two, so that they can increase their catch rates, because it's data coming to us, so we certainly want as much data. And they're identified with flags, so that our officers know that that person who might be fishing with an extra rod is in the program. So that's how we communicate that. Very quickly, and this will be important for some of the information that Dr. Munaweera is going to talk about, but in the past, we have used Floy tags or spaghetti tags as an external marker to identify fish, and that's for our population estimates. We since have moved away from that. There was problems with the readability of the plastic after a while in the river. We'd either get algae, or the numbers get abraded off, or they'd be lost completely. Now the volunteers are injecting subcutaneously a pit tag. It's the size of a grain of rice, and we've had much better luck with that. So that's what we're currently doing. The fish are measured for total length and fork length and girth, which provides us biological information on growth and other parameters. I just want to do a quick shout out to Jeff Krakowski, he's been in the program for 21 years and now is the volunteer coordinator. He's been a huge help to this program, and a lot of these photos, as you can see, it's photo credit Jeff Krakowski. He's done a ton for this program, so we've been very very thankful for his help. He's helped with communications, so developing videos to promote good handling of fish or conservation messaging. We had Minister Nixon out. He was our minister a couple of ministers ago, and he jumped in the boat with Jeff, not in our boat, and spent the day with Jeff, and Jeff toured him around, which was wonderful. So, and then Jeff's received the Queen's Platinum Jubilee Award for his effort and dedication to this program. So just summarize that a little bit. The Citizen Scientist program has given us over 30 years of data, which is it's huge. To do this within government would be very expensive, and just their expertise has really made the program successful. They're stewards of the species and eyes on the river. So when something nefarious is going on, I'll get a call, or they'll reach out to our officers, and it's been very helpful for making sure that things sturgeon aren't being mishandled on the river, which really good. They come with, skill, transportation, gear, and as Inesh is going to show you, their data is very useful. So I just want to talk a little bit about our population estimates to try to illustrate some of the challenges that we're faced with dealing with a species like Lake Sturgeon. So the simplest estimates are closed system, meaning like a pond where fish can't get in or out of. And it's nice to do an estimate over a short time period because you don't have fish dying of old age or fish being born and growing into the population. So it just sort of a snapshot in time, a short estimate. And so the early work was done by some of the big names back in the 30s and the 40s, 1930s and 40s, and they actually did them in ponds. They would mark a number of fish, drain the pond, and then count actually how many fish they had in the pond, and from that they came up with the mathematics around these simpler estimates. But with Lake Sturgeon, it's a little more complicated, or a lot more complicated, because we have a population that we've been studying for 30 years. So in the first year, you have these animals identified. In the second year, you'll have 2 years of animals, perhaps, and as you go through time, you get more and more fish identified, and in different years. So the mathematics get much more complicated. The fish aren't in closed systems like those ponds, and so they live in open systems. So we have immigration and emigration of fish, so they could move into the study area, which would increase their numbers, or leave it, which would effectively be like a death to the population estimate, the emigration. And then we have natural births and deaths over the 30 years. We have tag loss, as I mentioned earlier, which can affect our estimates pretty profoundly. And any sort of data issues. So if the tag numbers tend to be long alphanumeric numbers, and if anything's incorrect, then it's really hard to track those individuals through our database. So these are all the things that we're challenged with, and Inesh has worked on. So not simple. So doing science, it's important about repeatability and review of what we're doing. And as part of that, Dr. Gary White from Colorado State, international expert on population estimates, the author of MARC software, he was commissioned to look at our information and give us some feedback. And so he pointed out to us from his models to what we actually measured out in the field that our survival estimates were contradictory. Survival numbers were lower in the estimates than we saw. We saw 100% survival in a tagging study in the South Saskatchewan River. He suggested an enhanced program with a so-called closed estimate. So what we did was a month of intensive targeted sampling when fish move less, like not exactly closed, but as best we could. And these were his recommendations. And at the same time, the Office of the Chief Scientist found funding, and we brought Dr. Munaweera on with an expert panel to address this, just due to the complexity of these models. So yeah, so at this point, I will pass this presentation on to Inesh for his portion. Thank you.
Thank you, Stephen. Right. Okay. Hi, everyone. So first, I will give you a brief overview of the dataset we are working on. So our dataset, we have data from 1990 to present, because this study, the results I'm going to present here until 2023, but we already got data for 2024 as well. During the time, there are 3 years, 2017 to 2020. We don't have any sampling survey data during that period. And over the time, there has been a few different tags has been used. Some are external spaghetti, most are external spaghetti in the early years, and then metal tags and external strap tags, and the newly introduced pit tags, as Stephen mentioned. So from 27, pit tags have been in the system, and from 2012, pit tags have been exclusively used if the fish were found with or caught with any other tags. They will just remove the old tags and insert the pit tag. So 2012 onwards, all the fish captured will have only pit tags, unless it has been tagged previously and never caught after 2012. All right, next slide. All right, so this is some biological information. So we have fish even age up to 60 years old in our system. So most of the Lake Sturgeon are around 10 to 20 years old, estimated. And then total length of the fish is around 100 centimeters and weigh around 5 to 10 kilograms. Next. All right. So when we look at the data, early data versus the recent data, we see some differences in biological information. This is promising. Actually, this data shows early stage of recovery in the system. Now, for instance, if you look at 1990 to 1999, most of the fish are small in size. If you look, especially if you look at age estimates, you will see most of the fish are even less than 20 years old. Now, if you go to 20 to 29, you begin to see larger fish in the system. Now, if you look at again the age, you will see now there are more fish even more than 20 years old in the system. And if you go to 2010 and onward, we see in the system we have large fish and also small fish as well in the system. That means they are spawning, which is a great news. Stephen, next slide. Thank you. All right. So when we work on modeling, we have faced some challenges as previously mentioned by Stephen, and previous analysis also suffered from the same issues. The most dominant issue is the tag loss and the orphans. That means there were some fish who had scars or some signs of previous tagging, but they can't be correctly identified which fish that was. That means they cannot be matched with previous records, so they will get a new tag. Those are called orphans. So either the tag is lost or it has been faded. Especially this issue is very prominent with external tags, but after pit tags, this is not an issue anymore. So we really expect to have good estimates in the future using pit tags. And also they are our modeling. We always try to incorporate other we call them covariates, other biological information into the model as well. However, there are some measurement inconsistencies. For example, when they try to measure the fish, this year it might be say 100 centimeters, next year it's like 95 centimeters. So some inconsistencies in the measurement process, and also even in ages. Some like if the fish was caught this year, it will be say 10 years. After 5 years, it should be 15, but the record shows like 40. So it can happen. So there are some errors like that. And also some challenges inconsistent in tagging process, especially in the early years. There had been double tags. If we had only double tags, the modeling process is easy, and if consistent, but it hasn't been consistent. And after 2012, the tax has been replaced with new pit tax as well. So this makes the things challenging to use the full data set for the analysis. And also we have low recapture rate, especially in early stage of the survey. Next slide. All right. So let me introduce you this Jolly-Seber model in very briefly. Jolly-Seber model is the most widely used mark recapture model for open populations, because in this population is, as Stephen mentioned, open. We have immigration, and also births and deaths in the system. So now the Jolly-Seber model to be adequate, there are some assumptions to be met. Now, one is animal retain their tags, which is not the case in our study, and tags are recorded correctly is another assumption that is required, and sampling is instantaneous. So this assumption is according to studies is less serious than the other violation of other assumptions. And also survival and capture probabilities are the same for all individuals, and also the study area should remain constant over the time. Next. All right. So because of those assumptions, we have to make sure at least the most of the assumptions are satisfied. So we use only pit tags for the initial analysis. So the results I will present here are based on pit tags. Now we have data from 2007 to 2023. And as I mentioned, we have some missing years. So you can see the spread of the pit tag sampling locations. It represents the entire population of Lake Sturgeon inside the province. Next. All right. So to estimate population parameters, we use pit tags from 2012 to 2023, where we had most data. Of course, we had those missing years as well. We used the RMark package that Gary White also used, and we used the maximum likelihood approach. And the surveys were condensed to annual event, even though the surveys has been gone for a few months in each year. We condense all together to improve the recapture probability estimates. And capture probabilities were set to 0 for the years when no sampling were conducted. So this is more of modeling information. And as for the parameters, we assume that the recruitment and detection probabilities to be time varying. That means for each year they can be different, but we assume the survival to be fixed throughout the time period. Next. All right. These are some results. So initial modeling suggests that the survival is around 0.87, which is pretty low for a species lives this long. But there's a explanation for this, because the system is not closed. There are migrations out of the system, and that also contribute the apparent survival. So this is called the apparent survival. All right. This apparent survival does not only represent the mortality. Okay. So and capture probabilities. So we don't have any recaptures in 2018 to 2020, and population size estimates suggest that the population is stable around 5,000. But again, since we don't have we have missing data situation in 2018 to 2020, we have issue. The model still suffers from non-convergence around that period, and also the other parameters like recruitment probability also didn't converge well. Next slide. So we perform a simulation study. So the idea was to evaluate the performance of the fitted model, and also we wanted to inform the planning of future monitoring, so that we can expect some better estimates in the future. So we assume a superpopulation size 12,000. So superpopulation is the population from which the individuals will enter the system. This contains all the individuals that can be born into the system from during the study period. And we assume the survival probability to be 0.9 and it's fixed to the time interval. And so we define entry probability so that the true population size is around 5,000, like what we saw in our data set. Next. All right. So these are some simulation settings we use. We actually tested more than these. So the idea of the simulation study, different scenarios here, is to test out how different scenarios would affect the model estimates. For example, scenario A has a moderate effort through consistently through the time, and also scenario B kind of random efforts, and scenario 3 represent the it's kind of mimic our setting. We have missing years, but during some years the effort has been higher than the other years. Similarly, we tested some other settings as well. For example, instead of doing annually, what if we go biannually or triannually? And also scenario I, this is kind of extreme case because this is very low recapture probability, around 2%. In our case, we have around 6% recapture rates estimated for our study, but this is even lower than that. And also we tested the scenario G. So if you see a scenario C, after these missing years, there had been a large spike in the effort. And they have been tagging a lot more fish after this missing years, but this one is just simulating what would have happened if they didn't capture or tagged that many fish. And similarly, scenario H and I, those are future surveys. So we try to see, okay, if we want to, whether we want to go all in and again do very spend or put a very large effort on collecting more samples, or is it okay to keep the sampling effort to a moderate level? Next. All right, so we did this simulation that each scenario was repeated 500 times, then 500 models were fitted, and we look at the estimates. Pi hat is the survival and n hat is the estimated population size. Now, for each year we have a population size. So this population size bias and RMSE, they are the annual average bias and annual average RMSE. So by looking at these errors and also studying how they studying the distributions of those estimates, we could come up with some interesting conclusions. For example, you see this scenario F is the worst, obviously, because it's consistently low recapture rates. And scenario A, even though the effort is not very high, is consistent to the time, to the period, and we see a very small bias and variability in that estimates, which is kind of the best scenario out of all. Next. All right, so some overview of the results. So our initial findings suggest that the catchable size population in the study region is around 5,000, and annual, I would say, apparent survival is 0.87. And also consistent annual sampling yielded better estimates according to our simulation study. And low recapture probabilities caused increased variability and convergence issues in the model, and increasing sampling effort after subsequent years mitigate the negative effects for earlier data gaps like the one we had in our data set. Next. All right, so we are working on a little more advanced modeling framework called Bayesian hierarchical modeling. So the idea is to model to use a more sophisticated model that can account for tag loss and incorporate measurement errors. Now, this is still in progress, and as we get more data, we already got 2024 data. So we are working on these models to further improve the estimates. And now I will pass back to Stephen to give you the concluding remarks. Stephen.
Thanks, Inesh. Yes, so the next steps for conservation. The good news from Inesh, we've got reliable estimates. The next steps we want to do is publish that sturgeon modeling work, get it out in the scientific literature for review and communication. And we want to do a status update. We're seeing increasing numbers of fish. The numbers in the South Saskatchewan River were done in 2016, but it looks like numbers are building there as well. So we want to have a status update, bring together experts and stakeholders, and look at our recovery objectives and population goals. And reassess the South Saskatchewan, as I said, it's been since 2016. And we do all this work. We liaise with other jurisdictions and the federal government. As I demonstrated, the provincial boundary doesn't stop the sturgeon. So to summarize, overall good news and increased numbers, which is really great. We've confirmed that our methods for monitoring through Inesh's work are good and are giving us solid data. And we need to confirm our recovery goals moving forward here. So just quickly, acknowledgements once again the citizen scientists for all the long hours they put in collecting fish for us. Federal Fisheries has helped us with equipment and input, that sort of thing. The ACA has provided funding for the citizen scientists to offset some of their costs. Our partners, the North Saskatchewan Watershed Alliance, they've helped us out on some things and working on the river as well. The Office of the Chief Scientist for the grant to pay for some of this work, and then the committee members helping us out with this complex modeling. Doctors Mark Lewis, Laura Cowan, Andrew Paul, Mark Posch, and Lisa Schabel. I encourage you to go onto our website if you want to read more about the work that's being done on Lake Sturgeon. I believe that'll be put into the chat if you'd like to see more. So with that, I'd be happy to try to answer some questions if there are. Thank you.
So with that, I'd like to thank everyone for joining our science seminar today and providing such excellent questions. Our next science seminar is going to be on Tuesday, February 25th, and it's going to be with Dr. Mark Louis Lopez and Dr. Avi Dersch, and they're going to be presenting on reconstructing a century of change in lake ecosystems, insights from environmental DNA and indigenous knowledge. If you are not on the mailing list for these science seminars and would like to be added, please contact our office, and you can do that at epa.ocs@gov.ab.ca. I'm sure Leanne will toss that into the chat box window so folks can just click on that or copy that. And with that, I'm going to end it by thanking our two presenters again, Dr. Munaweera and Dr. Spencer. Thank you so much for a great presentation, great questions, great dialogue. Thank you both very much. Have a great afternoon, everyone.
Thank you for the invitation.
Thank you. Honored.
Bye.